Okay, so today, here's what I want to do. Yesterday we started doing something in programming language. Doesn't matter that it was C actually. The point is that I was trying to show how to think of image processing in terms of a low-level pixel by pixel operation, because I just strongly believe that actually helps you understand the foundations of image processing, which I believe is quite important when it comes to retouching, when it comes to digital artistry, and it just gives you like a general understanding and knowledge of the topics involved. Now, my main idea is that we are going to do some LUTs. However, we couldn't get to that last week in that 3 hours, because we were exploring different avenues of saturation or mappings. But this is what we are going to be continuing and actually turning those into useful LUTs that we are going to be able to use eventually. It won't even take that long, but I thought that we could do some sort of a small recap into how we were actually doing that. So I'm actually going to open Photoshop because I want to start by showing something. And just as a recap to all these things, it's opening up. What is coming up here? Okay. It says, wow, look at this. Look at that. It says Photoshop must quit because you're not signed in. Wow. I don't remember the last time I saw this. What is going on? Okay. Well, let's just quit it, because that's what he wants. Let me just try to reopen it. First time seeing that. Let me see Creative Cloud. I thought I was actually logged in. Let's see. Am I logged in? Am I not logged in? Oh, okay. Well, let me put this on the other monitor, sorry, just so that I can log in. Give me 1 sec. I didn't expect this. This is technical difficulties. Which is, I think it's this. Whoa, why did you jump back? Oh, because that's the Creative Cloud app. Oh my god. Everything is not logged in now, apparently. That's very odd. Do I... Okay. 1 sec. Oh, I have to accept the updated terms of use, apparently. Okay, now it's gone. Okay, now we can do things. Wow. Why did that happen? That's so odd. Adobe. I guess they released maybe new terms and that just bumped me out or something. Whatever. The point is that I need a new canvas. So give me a new canvas, please. That's fine. Just need a new canvas, generally. Actually, that's what was dumb, but whatever. So new canvas. Let me just zoom in. So here is a recap of what we were doing, okay? Let me grab a brush. That's not as big. Okay. Oh, you know what? It's fine. I don't know what this is. Oh, it's called streaks. That's okay. So what we were doing is that we were essentially looking at an image, right? This is an image. We were looking at the image, and images are made up of pixels, as we all know. And those pixels are the foundations to how we can actually process these blocks that we call images, right? Blocks of pixels. What we need to do essentially, and that's very, very basic and very, very simple, is that we take 1 pixel at a time. So there are many pixels here, one next to one another. We take 1 pixel at a time, right? And then we process that in a certain way. We do some operations on it. And what we were doing the last time, which is very, very simple, is that we took this pixel, right? This is a pixel. We broke down the pixel into its elements. Let me actually use other colors. So we broke down the pixel into elements of red, and then just to be very thorough with this, red, green, and of course blue. Oh, this is not very visible, but this is what we broke the pixels down to. So the red value, the green value, and the blue value. Of course, because we were working with RGB images, which most images are RGB images nowadays. Especially, I think like we could say like even 98% of the web is definitely RGB, if not more. And then we broke that down, right? We broke those down, and actually, I'm going to grab like an actual brush so that we can definitely see stuff. And we did some operations, right? We did some operations on these channels, which resulted in something of a different pixel. And then those pixels were actually put back into the image. This is what we've done. This is the circle of life now. We put those pixels back into the image, and we created a new image. Now, I think I still have in my recents, because recently I was, oh no, wait, this is the one. Yes. So these were basically the results that we got, which is called a saturation map, which is basically what it means is that it maps your saturation to your brightness value. So if I actually, let me just clamp this down just to remap these values. Actually, I'm going to like over map this just so that it's visible. So anywhere where it's dark, like look at the lamp here, which if you can recognize this is a LED panel. It's completely black because it means that it has no saturation at all. But anywhere else where it's brighter and anywhere else where it's actually white, then it gets to higher and higher saturational levels. So it just tells you and gives you an idea of like, oh, so this is my image and these are the saturational values, because by themselves they're very difficult to recognize, and that's why we use these tricks for this, right? And that's what we did the last time. Now, last time I know I made a mistake, and I was just, as I said, it's when you stream, your brain is different. It's not, your brain is not on drugs. Your brain is on streaming, which just makes you forget things. Immediately as I turned off the stream, I realized my mistake because I was leading up to like a finale, and I couldn't actually bring it home because I made a stupid mistake. So what we were working with actually was something called an LCH or HCL, they are backwards, whatever, color space. And in that color space, I was mapping the chroma value, but I didn't normalize it. I just had to like divide it by 180, but I didn't because I was stupid. Anyway, so we made these flat images, right? We made these flat images. Today we are going to make LUTs. LUTs that we are going to be able to use. Fantastic. Yeah, I'm going to try to make it, again, as informative and as easy to follow as possible for people who either don't care about programming, and for people who don't care about code or don't understand programming or don't understand coding. Doesn't matter. I'm going to try to make it as simple as possible, and feel free, as always, just to ask the questions. I'll try to answer them in a way that makes it easy to understand, if I can. Okay, let me actually, I don't need that. I'm just opening some stuff. So I need what do I need? I need, just give me a terminal. Oh, and let me know if I'm ever very quiet. I remember like a few streams ago, maybe like 10 or 12, which is last year, I turned off my compressor, and I shouldn't have. And that's why I was actually trying to set up like the beginning of the stream, but I couldn't find the right settings now. So I have to set it up the next time as well. But the last time I was listening to my own stream, it didn't, like sometimes they have very quiet parts. So just let me know if it's very quiet. And I apologize. So I needed this, and I think it was this folder. And I'm going to open VS Code. Right, so we were right here. Do we have... Hey! Hey, Ricardo. Hey, Elton. Elton, how are you doing? I might put this here. Yeah, okay. Let's choose from all of these. Let's choose just Photoshop. It's going to be fine. So we are going to be using Photoshop. So we don't need the terminal now. I'm going to turn that off. And yeah, so this is what we've been doing. This is what we've been doing. I know it's very, again, if you don't understand programming, that's fine. I'm trying to make it as easy to follow as possible. I actually was doing some other stuff here. In the meantime, I was working on something else. I can delete all of that. I don't need that. We were working on exactly this. So the first thing we were doing, this is important. The first block was we were loading in an image, right? Just loading in a sample image. Second part was we were doing some processing, which is this long thingy. I was just double checking some stuff. And the third part was we were just saving the image. Again, you don't have to understand the code. You just have to understand the thought process. We don't care about, code doesn't matter if you don't understand it. It's fine. Do you need to watch the last lives to understand this? No, I don't think so. This is still the recap of everything. So that's what if you're watching this recap, you're probably going to be able to follow today's stream. And this is it. We were coding, and that's why I was saying like a couple seconds ago is that we were basically making images like this. I actually should have. Let me actually open the whole thing. I should have like a layered one, a layered version from my projects, and I think. Where is it? That's not it. Sorry, I'm just trying to find it. Give me one sec, so that I can give you a proper. Yes, this one. So this is basically what we produced at the end of the stream, which is, if you look at it, a very wacky image. But what I did is that into the channels, I packed into conversions. What I packed into, the red channel has a RGB to HSL conversion. Using that as a saturation map. The green channel has an RGB to HSV conversion, and that's output as a saturation map. And the blue channel is the trickiest one. Is actually we converted RGB to XYZ, we converted XYZ to LUV, and then we used LUV to model that on a cylindrical projection. And that's called an LCH or ACL or HCL, and and that's what we see here. We were discussing the differences between different color spaces and the influence they have on saturation, and we were outputting that as a saturation map. Now today we're going to take that a step further, and we are going to use these to create LUTs that everyone will be able to use for their saturational mapping needs. That's what's going to happen. All right. I'm going to leave this up here just so that it's visible, and if there are any questions, maybe later, then I can answer those using the image if I need to. But hopefully, Elton, I think that gives you like a nice recap here. And as I was saying, you don't have to understand code. What I'm doing here, I'm just trying to make it very, very simple. As I said, we were loading in the image. This is a block here. We were doing some processing, and then we were saving the image. Now, this is what we are going to kind of rewrite here, right? Because here, let's explore what a LUT needs, right? Let's explore what actually a LUT is, because it's so important, and it's so actually very, very simple. It's the simplest thing in the world. Well, probably not the simplest thing in the world, but it's very simple. Let me go and open up a LUT of mine. Let me see if I can show you what it looks like. And I already showed this a couple times on stream, but it's worth repeating. I'm going to my LUT of the week thingy. I think that's the easiest one. Let's open the one that I call film curve. Okay. So I'm actually, I'm actually going to open it here. Hopefully this is visible. Now, let's break this down. What do we see here? We see the first line saying hashtag created by and my name. And again, hashtag, website, blah, blah, blah. Now, hashtags, the lines that start with hashtags in LUTs, this is just a text file, essentially. This is a LUT, but this is a text file. Those are comments. Those do not matter. So when LUTs get loaded in, you can think of them as like they don't exist. Like if I deleted them, right? These hashtag lines, they don't matter. They are just there as comments for us developers to know what we're doing. Or if someone wants to like open your file and they want to see like who made this, then you can put your name there like I did. That's fine. However, what LUTs consider, not really truly, but they can look at the title line if they want to. Photoshop chooses not to be honest, but they can. And what they also look at is the LUT size. Now, it says 33. However, if we look at all the lines that we have here, I mean, it's a couple more than 33. The reason for that is because it's 33 to the power of 3. So it's 33 times 33 times 33. Because it's a cube. We need to treat it, the size, as a cube. So that's why we need to raise it to the power of 3, right? Now, these two lines are optional in a LUT. These actually tell the software interpreting it as like what sort of a range it can expect. It is usually a 0 to 1 range, right? So 0 is black, 1 is white, or 0 is no value, 1 is full value, if you'd like. That's fine. I didn't delete this, but this is also a comment, so this doesn't matter. And then all these other lines are the LUT data. Now, the way the LUT works is that these are actually just RGB values. So this is, it depends on like what is usually the fastest changing value, but normally I believe it's like red, green, and blue next to one another. So red, green, and blue, red, green, and blue, red, green, and blue. In themselves, they don't really mean anything, right? You could be saying like, okay, so it's a lot of colors thrown after one another, which, you know, you'd be very, very much a sane person saying that. And you know, that makes a lot of sense saying those things. However, you have to think about it in a way that you almost have a neutral image in the background. So think of a neutral image, like a very neutral image, like a mathematically, scientifically neutral image. And then think of these numbers as numbers that will transform the neutral image to these specific values that you see in front of you here. Right? So if you have a pure black, what is that going to be transformed into? And that is what the LUT will tell you. It will look this up. That's why it's a lookup table. It will look this up and be like, oh, so I have to transform complete black into what? Well, by this logic, this is probably the complete black line, the first one. So what do we transform the complete black to? Because everything is 0, probably complete black. Now, let's see if we actually change the white. So let's look at the last line. Oh, look at this. Look at that. This is probably the line, because this is the last line. This is the line that would transform pure white into what exactly? And it would transform it into this certain color, which is 0.96 and 0.99 on the green and 0.95 something on the blue, right? So it's an off-white. It's not a perfect white. And this is what this LUT would do. So if you were to put this LUT on a completely white image, you would probably get something that's slightly darker, because it transforms those white values into exactly this, right? So that's very simple. Black and white values. You understand that, I think. It's a lookup table, looks it up. What do I transform it into? That. Simple. What about the in-between colors, right? Well, we have a couple lines here. We have a fair, like we have what, like 36,000 basically. We have 36,000 different colors that it can look up in this table. But we have more colors to work with, right? Depending on your depth and everything, you technically can have, well, way more. Let's just say that, you know, way more colors. It could be even like in the trillions, right? So how does that even work? Well, again, it's somewhat simple once you understand. If the color that it looks for is present in this table because it lies on a certain grid, like we have it in the table, right? Then it just picks it. So let's say we are looking for this one. Excuse me. So we're looking for that value, whatever this color would be. Let's say this transforms a particular bright red color, right? Let's just say that. And it finds it exactly in the table, then it will just use these values and it will just transform that value into this particular value. Now, if it cannot find it in the table, precisely because it would lie in between, it will fall in between two values. Like let's take these two lines, right? And let's say that value that we're trying to transform, that color that we're trying to transform, would actually be somewhere in between these values, right? On this table. Then what it will do in a very, I'm going to explain it in a simple way, but it's actually slightly more complicated, but the idea is the same. But what it would do is that it would look at both of those colors and it will interpolate, depending on what sort of a software you use. It could be a trilinear interpolation, so basically a linear interpolation 3 times, or it would be using tetrahedral interpolation, which is a 3-dimensional interpolation based on the geometric shape of a tetrahedron. The point is, it interpolates between 2 colors. So it looks at the two and figures out what would actually go in between, no matter how big that gap is. And then it just transforms that color into that interpolated, particular, specific color. So that's all what LUTs do. It's like there is no magic to them. The only reason that they are so very, very good and so very, very useful, and I spend so much time talking about them, is because even though they are so simple, they can contain like a huge amount of information because of all of the 3-dimensionality. The reason they are called 3D LUTs, right? And just to briefly mention this, if you open up a curves adjustment layer, right? A curves adjustment layer, this wouldn't be 3D. Because we are not able to transform colors in a different like a 3rd dimension. We're only able to make certain channels brighter or lighter, or brighter or darker, right? Or overall, we lack the freedom to have that 3rd dimension that would possibly be, for example, some sort of a matrix or some sort of a hue and saturation that is based on some smooth steps, color picking, or any of those things, right? That's things that are more specific. Like think of like adjustments that are more specific than curves, less global, more local. So this is a lot. Now, the reason that we needed to talk about last time how to transform colors is first, again, as I said, because it's useful, but second is because LUTs do the same thing. So now that we actually gone through all of those things the last time, we went through all of those steps, we just need to repeat them with a slight nuance, and we'll be exactly where we need to be able to create LUTs for ourselves, like any sort of LUT. And it's going to, in that sense, it's going to be very simple. Now, let me pull up my handy guide here, because I like to prepare for these live streams, even though it doesn't look like I do, but I still prepare for them. And I prepared for this as well. I'm actually just trying to find where I put this, just so that, you know, everything can go quite smoothly. And I want to put this on my other monitor here, so it's easy for me to double check what I'm saying. Okay. All right. Now, as I said, because we are about to generate LUTs, we will not need to load in an image, which was our first section in our code. Okay, don't worry about what the code does. I mean, what the specifics of the code are. Just understand that it loads an image. We will need the processing part because that will always be needed. And we won't need to save an image because we will be saving a LUT. So I think I'm going to recreate this file. I'm going to create a new one that I'm going to actually call lutgen.c is what I'm going to be calling here. Now, this is where we are going to operate. Let's just, this is, the important parts. Return 0. Don't worry about these. These are just like boilerplate stuff that we need. This is the file that we are going to be using. I will have to probably work on this a bit more. Here is what we need to do. The steps. Let's outline the steps that we are going to take to generate our LUTs, right? So the first thing that we are going to do is we are going to what should I call this? We are going to not give information. What is it? Like set some constants, basically. Set some constants because we want to set like some sizes. We want to set some. We maybe want to set a title. We want to set something that's like more of a what this LUT is about. That's what we want to do. And then the second step is going to be formulating the LUT or even like calculating the LUT, right? Calculating the LUT. And then the third will be just saving the LUT. So these are all the steps that we have to take here, right? I know it sounds very simple, and it actually is. But I need to try to make this easily comprehensible. Again, I keep repeating this, but for people who don't care about coding, and it's fine. We don't need to. Whatever. All right. So as I said, the first thing that I'm actually going to do is I'm going to create a variable called title. Now, if you remember, if I switch here, it's going to be this line exactly. We are just going to set a title. It's not that important. I'm not sure. I need to check the specifications if it is actually mandatory or not. But we're going to set a title. So our title is going to be for now. LUT. A stream LUT, just for now. We can always change that later. It's going to be fine. So we are setting a title. The second thing that we are going to be setting is actually going to be a size. So let's just set a size here, which is going to be, well, I don't need the quotes. Let's just do like a small LUT. A small LUT is usually, at least what I consider a small LUT, is usually around like 32, 33 data points, which is, again, you need to cube that. So that's actually going to be 32 times 32 times 32. So that's what we're doing. We are setting a couple of things here, right? Now, then we will have to set some other stuff. The reason we need to set some these other stuff is that there is a certain pattern that we have to follow to be able to save out the LUT, right? To save out the things that we need to save out. So this isn't going to be as exciting as writing the title and the size, which was amazingly exciting, I know, but we still need to do certain things because what we're going to be doing is we are going to be putting all of our data into, think of it as a single text block, right? And once we put everything into that text block, just like we have it here, right here, we're going to save that out as a .cube file, and then we're going to load that into Photoshop and use that in Photoshop. But in order to get that, we need to do some, programming stuff, unfortunately. But let me get through that quickly, and then we'll get to the calculating the LUT part, which is the exciting image processing and fantastic part of the process. So let me just quickly type this out. And what it actually is going to be is we are going to need a float pointer, which is going to be our data. And I'm going to actually cast this into that, and we're going to do this. It's going to be probably the size of float. I'm also just somewhat just copying it from my other one. Size times 3 is what we need. And for that, I will need to include std_lib.h and do that. So what I'm doing here, again, I'm just basically explaining it just so that you know it's not just you staring at the screen. I'm just allocating some memory for the data that I want to store. That's one of the things that I'm doing here. Now the other thing that I'm about to do here is I need to allocate some. How did I do this last time? That's what I'm looking at. That's a different thing. Yeah, so that was for the data, right? Allocate memory for data. And then let's calculate size of header, which is going to be a constant. That's fine. Header size. And here is where it comes into play. Here is where we need to count things. We need to count the title, which is 1, 2, 3, 4, 5. We have a space, so that's 6. And then we have a new line character. What was it that I said? 1, 2, 3, 4, 5, 6, and that's 7, right? And then because of all of that, we also need this thing that I want to include, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 plus 7, that's going to be like around like 20. Let's just add a bit more, just a padding, because if I don't want to mess up the calculation. So let's just do this. And we're actually going to measure the title itself. String.h. That's what we're doing. We're just calculating how much memory we need to have in order to fit the header. And I'm calling this, that is not the data, all of these lines, the header, right? This is the header for me for now. Is what it is what I'm calling. So that... Oh, this wrong one. So this one. So I'm calling that a header. The other thing that we'll also need is we are going to need to calculate. What was that? Yes, calculate the full LUT text size technically. So we need to calculate how much actual, size and memory we will need for the whole text itself, the header and the data together, right? So we have the data up here, we have the header size, and then now we're going to determine the size of the, the whole text size, whatever. So I call this, let's call it LUT string size, where it's going to be, we are going to use the same exact thing as up here. So size times size times size, because as I said, it's cubed, plus 3 because we have 3 components. Then we are going to actually, oh no, we actually don't need the components here because we are going by line. And then we are doing strlen here. And what I need to do, here is what we are going to do, 0.000000, right? That's what I need. So we're taking the size of this, because this is going to be a single line, right? We are taking the size of this, and we are adding the header size to that. We are just calculating, again, like the full size of this file, like how big this file is going to be. Not very exciting part, but let me get to the more exciting part. I know I'm making a lot of excuses here. It's going to get more exciting, just believe me. It's going to be fine. It's going to be way, way more fun. Okay, and now that we have the size, we are just going to allocate memory, which is going to be just a char pointer, and it's going to be the LUT string. And let's just cast this into chart pointer, and we are going to call malloc, and we're just going to use the calculated size, the LUT string size here. It's fine. So this is again, this is not something that you need to concern yourself with if when it comes to being a digital artist, when it comes to understanding LUTs or anything. This is for the coding side. Everything else that I said before that is actually about more of that, the actual stuff. So let me do some extra comments so that everyone understands where these sections begin and end. Okay. So let me do all of that. Right. So this is just a setup, sort of a thingy. Now in the setup, the last thing that we have to actually do is we need to have like a cursor position. I'm just going to use a cur, and that's going to be 0. This is for tracking something, and we are going to now print out. Actually, you're going to need that as well then. Include stdio.h. So, oh my god, you messed this up. But what we are going to print into that is we are going to print into the LUT string using the remaining size of the LUT string size. And what we are going to print here is the title. We're already doing that. And what I want to do is this, then a string, then that, and a new line character. So we are printing the title there, and also we are printing the what is it? We are printing the LUT 3D size is what it is, right? Yes. I'm just double checking my own thingy here. This is what we need, and we are putting in the title and we're putting in the size, right? So that's all. That's what we do. We're almost done with the boring part. Almost done with the boring part. And hopefully I'm doing it well, because otherwise it's just meh. Okay. First part, setting up some things, right? Second part, getting onto the second part. Let me do these lines. And again, any questions, just let me know. I know this is, you know, the necessary evil of what we're about to do. So, here is where the interesting things comes in. As I said, if you look at these, the data points, right? And I said that imagine a mathematically, scientifically neutral image. I think these are the words that I used. The way we are going to do that, actually, the way we are going to somewhat create that in the background is going to be akin to a child counting from 0 to whatever number. Or anyone counting. It doesn't have to be a child. I don't know. But for some reason, I was thinking of like people, you know, like kids, like playing around by counting and everything. Like they can count like, oh, I can count to 1,000,000 and all those things. That's what we are going to do now. We are going to purely count from 0 to 1, except we are not going to only count once, not even twice. We're going to be counting 3 times because we have 3 channels. So all 3 channels are going to be starting to count up from 0 to 1. Right? So from 0, we are going to be counting up to 1. I know it sounds weird, but, you know, because we are dealing with numbers that are floating point numbers, we can actually go to 0.1, 0.2, 0.3, you get the idea, right? That's all you need to do. Well, that's how we are creating a pure image, by going through all the numbers. And by going through all the numbers, we are technically creating a very, very colorful image. We are just not going to save that as an image. We're using that as a data point. So in order to do that, we need to create some loops. Now, loops in programming are things that they run until they are told not to, until they are told to stop. And what we're going to do is we're going to say like, hey, please start this loop at 0. And this is going to be the blue loop. So I'm just going to call it B. That's the blue loop. So please start from 0 and run until you get to the size of my LUT, okay? So that's going to be our maximum. Please run until you hit the size of the LUT. And every single loop, please increase it by 1. That's the first loop. Now, inside this loop, we are going to start the second loop, and we are going to be like, hey, please, G, which is going to be green, not G, not the very cool name for our friends, like, hey, G. Oh, I know, it's very cool. But that's not, that's not it. It's just for green. Why am I so weird? No one knows, right? But that's for green. So hey, green, please start from 0. And green, would you mind going up until the size that we designated? And every single loop, please, green, increment yourself by 1. Again, that's another loop, right? So we are incrementing blue and we are incrementing green from 0. Now, the third loop, you might have guessed, is going to be red. I'm going to call it R, right? Just the letter R. Please start from 0 as well. Do the same thing as the others. So go until the size of the LUT that we designated up top and increment it by 1. So now we have 3 loops inside one another. Very simple idea. Again, just think of it as like counting for this purpose from 0 to whatever size we are able to count to, and then stopping, right? That's what we are repeating constantly. So anything I'm writing inside of this, because like technically like underneath, if you're not familiar what inside means here, but inside is technically just inside these, it's not square brackets, just like curly braces. Inside these, they are going to be repeating or like again and again and again, right? And what we are going to do is we need to keep track of their index. So I'm going to create a number up here called index. I'm going to set it to 0. So before we start with all the counting, we are starting at 0 index. Okay, bear with me. Here is where the fun part begins. Now here is where we are going to tell the LUT how to LUT, what to look up, what to do, how to transform, all of those nice things. Here is where all of that happens. Okay, so we are going to make this into a very, very simple kind of an, let's just translate it into sort of English, right? Something that we understand. So we're going to say float red. Now we are calling it red. Make the red value. We are using R as the first one, and we're going to divide that by the size of the LUT minus 1, right? And this is just because of programming. I'm going to cast this. It's fine. Okay, please don't do that, because that's just makes it unreadable. So that's what we are doing. So we are going to say like, hey, red value should be our R, as we are like counting the R up divided by our size. So that's how we are going to normalize this. And then we are going to say the same thing about all of the other ones. I'm actually going to copy these lines, and I'm going to say, hey, green, oops, I can't type, make that G divided by the same thing. And then the blue here should be the B divided by the same thing, right? So here we are just normalizing the values, because remember we said that, hey, B, start from 0 and then start counting up by 1 every single time until you hit the size, which is 32 that we designated up here, right? Now if B starts to count from 0 and incrementing that every single time by 1 and only stopping around before it gets to 32, then it will be like 0, 1, 2, 3, 4, 5, right? You get the idea. But what we need is 0 to 1. So we need numbers from 0 to 1. So we need to go and divide that number by the size minus 1, right? So very simply, we are just getting that, and we are just like, if you say 0, then we're going to say like, okay, 0, and let's divide that by 32. Then let's take 1, and that's 1 over 32, and then 2 over 32, and that kind of a thing. I mean, we have the minus 1, so it's 31, but you get the idea. And that makes it just normalized. So now we are in the 0 to 1 range, sort of. We can call it a normalized to 0 to 1 range. We're just normalizing the values to the 0 to 1 range. That's so simple. The second thing is going to be us just putting this into the LUT string that we created before. Right, so what we need to do first is, because we have the data, we can use that data variable and we can put that at the index. Now this is kind of a more complicated topic to understand, so just bear with me. We are just putting all these values into the appropriate places, is the easiest way I can explain quickly, and then we're going to print them out. So we are going to take this current that we already took, and we're going to actually add this, and I'm going to put this into the LUT string plus the current position, and the size is going to be the LUT string size as we actually set up there, minus the current position because we don't have any more than that. And actually, I am going to go and 0.6f, which means that we are going to go for 6 decimal places after the decimal point, right? So 6 is what, because we want this to be uniform. Like, look, this 0 could be represented as like this, right? Or it could be even represented as that. But we want to be very neat and just have like these nice columns. So 6 places after that. So space. Again, and we are almost getting into the part where we can mess around with the numbers and creating all sorts of weird LUTs, right? We just need to set it, like we need to do some setups. Just promise me it's worth it. What do I need to do then? We need to add, what is it? Oh yes, okay. So we need to add the red for now, the green and the blue. We're just adding that there. I don't know, I just had a brain fart. So that's it. That's exactly it. Now this, what we created here in this block, you remember, we incremented those numbers. We just started counting, right? We just started counting. And then those, incremented numbers got normalized. So now we are counting between 0 and 1. We are counting between 0 and 1. But still very uniformly, right? Very uniform distribution. And then we are pushing those numbers into our appropriate channels. So what do you think this will result in? This will result in nothing. In terms of, you can apply this LUT once we save this out, and this LUT should do exactly nothing, because our lookup table is going to be like, hey, make black, black, make white, the same white, make the same red, make the same green, and so on and so forth, right? And that's the LUT. It's still a LUT. It has these lookups where it's like, hey, do this from that and transform this to that. But because we haven't done anything, we haven't applied any sort of transformations yet, this is a pure neutral LUT. But this is the starting point that we want to get to, right? This is where we want to start from. Now, before we move on, what I want to do is I want to also save the LUT out so that we can actually double check that, and I can show you how this is a neutral LUT. So we need to quickly, I need to quickly write the saving out part. And again, it's another part that you don't need to understand truly. It's just going to be, the way you save things out in code. That's basically it. So if I can actually type, that would be fantastic. Let's just call it out. It's whatever. Let's call this, let's call this stream LUT. Just why not? Streamlot.cube, because we need that as the extension. It's a .cube type LUT. Let's just check if the file is actually appropriately created. And if not, then I'm actually just going to fail to open file, or fail to create file, actually. It's probably more appropriate here. And if that happens, we have to free the data, and we are going to actually free the LUT string. Those are just memory, so that we're not leaking memory. It doesn't really matter because the OS would actually clean it up, so don't worry about it. We were just saving up some memory, freeing up memory. And then we are going to write the string to file. So we are just writing the LUT data, the LUT string that we created, the LUT text, if you will, into the file. So, okay, just going to do this this way, and we need the LUT string, I believe. Yes, and then we need to close the file, and which is going to be close and out. We are just doing that. If we get here, we are successful, right? So we are going to write out success. So we got that, and we're also going to free the same things as we were freeing if we were to fail. Oops, right? The same thing. Okay, so this is the part where we save the LUT. Very simple. I know, I'm sure that you agree that it's very, very simple. Okay, we just need to run this thingy. I'm thinking if there is anything I need to set to run this. Let's try to run this, and then I'll just figure it out in the meantime. Let me just clear this so that it's much, much cleaner. Now I'm going to try to just run this and see if we need to debug something, if I mess something up, and if not, then I can show you what this does in Photoshop, and then we can move on, hopefully. Okay, exciting things. Let's just use Clang. I'm going to use Wall. I'm going to use we error. I actually want to do pedantic, so we're just going to do what is the name of this? lutgen.c, and we are going to make this into, what is it? lutgen.exe is fine. I think probably if I'm, oh, you know what? Let's just run it, and if I fail, I failed. It doesn't matter. So we have that. Have we created the file? Are we successful at creating the file? Yes, we have an exe file. So hopefully we can just run this, lutgen.exe, and hopefully, fingers crossed, we're going to see a success print out here. Hey, success! Look at that! Fantastic. Okay. Let me just look at this. We have the generated cube LUT here. Let's see what we created. Oh, look at this. So now what we have, as you can see, is we're starting from 0. We have the title here, just like before. If you can actually compare it to this one. I know we have a lot of new lines here, but it's just make this like that, so it's easier to compare. And I can actually do this. So right side is a LUT I released on my Patreon, and the left side is a LUT we just generated. We generated from just pure numbers and algorithms and everything. So from 0, as you can see, it kind of looks incremental, right? It looks uniform as I scroll down. It actually looks like counting, like very neutral counting. There you go. And the last one is 1. So technically, we are turning white into white, right? That's what it should be. And then the first one, we are turning black into black. Now, unless I really messed something up, which I hopefully did not, then if I loaded this LUT into Photoshop, not this LUT, this is the code itself. If I loaded this LUT into Photoshop, Photoshop would actually understand it, and Photoshop would actually not do anything with our images, right? It wouldn't really do anything because it shouldn't. Let me pull up like a let's just pull up the usual image of my wife, which is the I'm just trying the one that you see on the monitor, on the screen right now. I'm trying to remember where I put this. Let's just put something projects. Where is it? Sorry. I'm trying to be fast here. And utterly failing. Assets. Give me a neutral image. Is this a neutral image? Which one is the neutral one? Okay, this is the one. That's fine. Let's just open that here. And what I'm about to do is, let me quickly be kind of sneaky about this. Let me quickly just, I don't know so I'm adding a LUT, right? Adding a LUT. Let's just start with that. So this is, I added a LUT, a lookup table, adjustment layer. I'm going to load one, but I don't know where it's actually going to load from, and I don't want to break any NDAs. So give me one sec. Let's just switch to my stupid face. And let me try to load this. Let's see where it loads. And if it doesn't load anywhere stupid, I can like switch back. This isn't the one. Give me 1 second, please. Saturation LUTs, stream LUTs. Okay, I'm switching back. Look, so I'm switching back, and this is, I don't know if you can see this, but this is called the stream_lut.cube. So I'm just trying to prove that this is what we're going to be opening here. And I opened this, it actually opened, no errors or anything. And you see, the image is still the same. Like if I turn it on and off, if I turn it on and off, nothing really happens, right? Nothing happens. Even though we applied a LUT. We applied a LUT with a lot of these values, right? This is the grand finale of the first part of this stream. So, yay, we need confetti and everything. But look, this is basically what happened. Like we can turn it on and off and nothing happens. Because we created a LUT successfully and correctly, and it just works. And I can actually turn this around so you see that we are applying a LUT. I'm just like reversing the table order. This is just so that you can see that we are applying the LUT. This is the LUT on top. It's just currently in a wrong order because I turned it around. Like, let me just go back to the right order. Okay, fantastic. Fantastic. We are back to the right order. Okay, now here comes the actual fantastically exciting part. And I'm not even exaggerating because I am myself, I'm so excited about this. This is my favorite part, okay? My favorite part. We are creating the LUTs. We are creating looks. We are creating stuff. We are generating useful LUTs, hopefully, that we can use. Now I'm going to close the film curve LUT. I don't actually need this anymore. I'm not going to save this. We don't need to look at the stream LUT cube anymore. I'm actually going to close that as well. Oh, I didn't save that. That's fine. Okay, so we're back to our code here. We are back to our little code here. Actually, this might be even neater if I just pulled it a bit more, right? Because we have the space. Let's just have more of Photoshop. All right. So, as I said, this is the part where we are calculating our LUT. Now, what can we do here? Think back to the previous stream, if you were here, the previous stream, or if you watched the previous stream. And the point that I was making there, and the point that I was making during the recap, is we are going through all the pixels and we are applying some sort of algorithm that changes the pixels from one to another, right? That's exactly what we need to do with the LUT as well, but instead of pixels, we are changing data to something else. And then using that data as a lookup table so that Photoshop can be informed by our decisions and Photoshop will be able to display the LUT data. Now, the most simple, like the simplest thing that we can do, and this is what we did the last time as well, so let's start with this, is turning things black and white. So we are going to create a LUT that turns things black and white. The twist here, because it could be very, very simple, the twist here is we can actually, I'm going to introduce a couple different algorithms of ways of turning things into black and white. And then we can package that into like this. Let's say we can package 3 different algorithms, 3 different black and white algorithms into a single LUT, and we can use that LUT later for anything we want. Okay, so that's the first thing that we're going to do. But first, simple. Okay, how do we turn things black and white now that we have color? What we need to, because we have 3 colors, we have 3 channels, so we have red, green, and blue. What we need to do in order to turn that into black and white is we just need to take their average. So because the values that you have inside the channels are technically brightness values, so brightness of your red channel, brightness of your green channel, and brightness of your blue channel, all you have to do is you just have to average them and output that all of the average to the same exact channel, right? So you want to make all the channels uniform, and that's how you're going to get to a black and white image. Just like if you look into Photoshop, let's say I open up a hue and saturation layer, right? Now if I look in my channels, this is the red channel, this is the green channel, this is the blue channel, right? Now what happens if I start dialing the saturation down? Look, this is the blue channel. Do you see what happens here? Do you see how I'm pulling saturation out, not specifically from the blue channel, but I'm transforming the blue channel still in terms of luminosity, because we are starting to average. It's a more complex algorithm, but let's just say it easily. We are averaging sort of all the channels here. So I pull this down all the way, and now if I check out all the channels, they don't change. Like, the picture doesn't change. It's all the same. So we are making the channels exactly the same, and this is going to be the result, right? This was before, and this is after. If we look at the channels, everything is the same, right? The only bump that you see at the beginning is like when I switch to all the channels, which has to do with the gamma as well. That's why it changes a bit. But otherwise, the 3 channels are identical, except if I turn off the hue and saturation, then you suddenly see the red channel bump back into the red channel ways, and the green channel is like that, and the blue channel is like that. Okay, so that's what we're going to achieve first with the LUTs. That's the first exciting algorithm that we are going to apply. Again, it's very simple, very basic, not amazingly accurate, but this is needed to build to something. All right. So now that we have these values that we have here, right? Now that we have these values that we have here, what we're actually going to do is we are going to do an average. So let's just create we can create a const float called average, right? And that average, as I said, is going to be, so we are taking the red channel and we are adding it to the green channel, and then we are adding it to the blue channel, right? And parentheses, we are going to divide that by 3, right? That's a fairly common way to average things. Like, add all of them together and then divide them by the number of elements that you added together. That's a simple average calculation. Now we have the average, so we calculated the average value of the channels, and now instead of the red, green, and blue here, because here is where we are putting it into the string that we're putting it into, we're actually going to take this average, and we are going to start putting it into the red channel, we are putting it into the green channel, and we are putting it into the blue channel. So you see, all 3 are going to be the average. So let me just save this. I need to recompile, like rerun the program. I'm rerunning the program. And now, if I go into my color lookup, which is now turned on, double click, and if I reload the same LUT, hopefully we'll see a black and white image. Let's, fingers crossed. So let me just go into load again. Let me select it. And look at that. We have a black and white image. So all we did, and this is completely the LUT that we created inside like a programming environment. So programmatically, procedurally, we created, just purely using algorithms, a LUT that is already something that could be somewhat useful, right? If you don't have access to Photoshop, you only can actually use LUTs. For example, here in OBS, where I am, where this floating head of mine is and bust of mine is, you can actually apply LUTs, but you might not be apply certain transformations, right? So this is already something useful. Now this is a very simple conversion, using the average, right? So that's one way to create a luminosity or a black and white, if you will, a black and white LUT. So that's the one first thing. The second thing is going to be, we're just going to do something slightly more complicated just to ease us into the even more complicated things. And then eventually we are going to get to a saturation map packed LUT that we'll be able to use later for saturational mapping needs. It's just going to be that simple. Okay, so the next thing is, as I said, the more precise black and white. And I never remember the numbers, so I have to always pull this up. I don't need this. Sorry for the blinking. That's not what I want to do. So there are different ways of calculating luminance or calculating luma or calculating brightness values. There's so many different names and they actually all mean something else. Now, we are going to be calculating something called relative luminance for the next section. And relative luminance is basically looking at how the way the human eyeball works and the way we have our cones in there and how many we have and how sensitive our eyeballs to different wavelength of colors, right? How sensitive they are to the red wavelength, how sensitive they are to the green and blue wavelength as well. And it turns out that the eye is actually the most sensitive to the green a wavelength, to be fair, and the least sensitive to the blue. So we are very terrible at differentiating blue values, right? And different blue hues. We are amazing at green. We are the best at differentiating green. We're not the best, but we are very good. So that's what we are going to do. Now, I'm going to show you the wrong way, and then we're going to do the right way. And I mean, let me just show you. Let me just show you before I talk. So here's the wrong way first. So we don't need the average anymore, but I'm just going to leave that there for reference. Now the next one is going to be const float. It starts the same. It's just the way you program. You need to repeat a lot of stuff, and this is going to be called wrong relative luminance. Okay, I'm going to call it very long with a very long name so that it's easy to read. And I'm just going to copy this because I have this on my other monitor. It's basically the following, right? Let me just save this. So it's the following. We are multiplying the red by 0.2126. I'm sorry for covering it. And then we are also multiplying the green with 0.7152. And then we're multiplying the blue with 0.0722 right here. And then we are adding them all together. So this is wrongly believed to be the relative luminance, and I'll tell you in a moment why it isn't, but it's going to be very, very good. It's still going to be very, very good. Just trust me. Okay. So we are going to toss this one into, for now, all of the channels, just like we did with the average, right? So I'm just replacing all the averages there with this wrong relative luminance. So let me just save this and regenerate my LUT file. So I'm just regenerating it quickly. We have success. Nice. So I can just load this in and pay attention. Pay attention to the black and white that you see here. I'm going to do this, and I'm going to actually make this smaller so you can still remember. So just pay attention to the image itself. So double clicking here right now. Did you see the difference? Did you see the difference? There was a difference. I can't go back and forth, unfortunately, because it's the same file, but there was a difference. And the relative luminance, this wrong relative luminance is actually quite good. It's not bad. Look at the color chart here, the color checker. If I go back and forth, you can see how the colors that you somewhat perceive darker actually appear darker in this black and white mode. They actually do appear somewhat darker in this black and white mode, especially if you look at the blue square here. Look how dark that appears, and that's quite accurate, at least I believe. If you look at the yellow, that also stays quite bright. So that's what I mean, like how perceptually they look correct. So this is quite a good relative luminance. This is quite a good calculation for black and white mode, right? This is quite a good calculation here. It is what it is, though. Now, the reason I say and call this the wrong relative luminance is because technically the way you have to apply relative luminance to an image is first you have to linearize the image. So you have to eliminate the gamma. You basically need to turn the image into linear. That's the first step. Then you apply this relative luminance calculation, which is going to be the same as you can see there. And then you transform the image back to its original gamma, which in our case is probably going to be sRGB. That's a gamma. You need to transform it back, and there you go, right? So that's one of the things. That's just a very small difference, like a small nuance, if you will, right? But it's still a difference, and that's why I call it a wrong relative luminance, because I don't want anyone to believe that this is 100% the right way, because it isn't. The right way is to turn this into linear, then apply this calculation, then turn it back into sRGB. Now, the fantastic thing is that we can do that with LUTs. I told you this is building into something. Well, you can do that with LUTs with no problem at all, especially the way we set these things up. Like we can just write a couple lines of code, and then we already converted the image into linear. I can actually show you how. Very simple. I'm just going to copy my something that I prepared here. So let me just go up here. We are just creating a function, something that helps us. What is it? Something that helps us with the calculations. Okay. I need to include the math library, I believe, for this. No, math.nothing, math.h. We need to include that. And I'm going to include two functions that I've written in the past. So one function, first one, the top one that I'm highlighting, is sRGB to linear. So this is going to be responsible for turning our image into linear values from sRGB. The second one is linear to sRGB. So this can actually turn values from linear to sRGB. Right? Simple. So coming back to our processing here, I'm going to comment out, which means that it won't work for anymore, our wrong relative luminance. I need actually both of those lines to be commented out. So I'm commenting out the wrong relative luminance. And as an experiment, I'm going to call something a const float linear. I'm going to create linearized values here. And I'm going to call it actually linear red. And there will be linear green, linear blue. So first, let's turn our sRGB image from sRGB to linear. So we're going to use that function that I created up there, I highlighted. So it's going to be sRGB to linear. And I'm going to just type in the value here, which in our case is going to be red. Now let me create 3 copies. I'm going to just select red and just rewrite it to green. And on the third line, I'm going to rewrite the red into blue, right? So now what we created here, we took these channels, the normalized values, and linearized them from sRGB to linear. Did you know that you could do this with LUTs? Like you could just like go in, because you can technically do anything. You go in and turn sRGB values from, sRGB gamma to linear with LUTs. We can do that. And that's fantastic, because that opens so much more calculational possibilities, because we're not losing, it's just amazing. Okay. So now let's just load into, instead of all the channels having the wrong relative luminance, let's just load in the first one, linear red, and then let's load in linear green, and then let's load in linear blue, right? So let me just save this, and now we are done with the first phase. So I'm going to regenerate this. Let's just regenerate, and after regeneration, we are going to load this in. So it's going to be a huge difference, so we don't need to remember. But look, we linearized the values here. This was the before, this is the sRGB, and this is linear, right? You see how darker it is, of course. It's not something that is like straight away usable, but you can see how through the power of maths, we actually turn this sRGB, all the sRGB values into linear values. That's fantastic. Now, straight up, it would be very difficult to work with this inside Photoshop, and the reason for that is the calculations inside Photoshop. Like Photoshop still thinks that this image is sRGB gamma. It doesn't know that it's actually linear. It thinks that it's actually sRGB. So working with this would be quite weird. But this is not what we want. We don't want Photoshop to work with this. We ourselves, we want to work with this, right? As I said, we want to get to the right relative luminance. And the way we do that is first we need to turn the image into linear. I just wanted to demonstrate that it works and how it works, right? Now the next step is going to be us. Let's go back to code. And now that we have the linear values, I can actually just copy this top line here, which was the wrong relative luminance. I'm going to uncomment those lines, and I'm going to actually call this not wrong, but actual relative luminance. So just simply relative luminance. But now instead of red, green, and blue, I'm going to be using linear red, linear green, and linear blue. So we are using the linearized values for the calculation now. I know it's very weird to read on these like multiple lines, but it's fine. We'll get over it. And then this relative luminance, because now it would basically be something like, and again, I'm approximating, but it would be something like this. So you would still see the image in linear. We just turned it black and white, right? We need to turn this back into sRGB from linear. So after we had we made these calculations, the only thing that we have to do is we need to const float. I'm actually going to not write const because everything is so long if I write const. That's just, sorry, just so that it's easier to read. So I'm going to write float and sRGB rel luminance, okay? So now it's the sRGB version of the relative luminance, and all I have to do is apply that lin to sRGB function that I made earlier, and I'm just going to put in the relative luminance that we calculated, okay? So the first step was here, linearize sRGB gamma values, right? That's the first step. Second step is actually calculating relative luminance using linear values, right? That's what we did. Third step, which was the third step, was converting linear values back to sRGB gamma, right? That's what we're doing. So now this sRGB relative luminance is something that we are going to display in all the channels because you know that's black and white. All the channels are the same. So in one channel, in two, and all three channels now. Now, if I regenerate this, hopefully everything will be fine, but why wouldn't it be fine? So now I regenerated this. Now I'm deleting this UN saturation. So this is what we had before. This was just the linear values. Now we are loading in the actual correct relative luminance. Ta-da! I know it's it's mind-blowing in terms of a transformation, but we created something that's actual image processingly correct, right? And I think that, you know, that just makes me feel good. That just makes me feel good in the sense that we are going through this process understanding and being aware of what we're doing. We're not just like turning knobs. We're not just clicking on things. We actually know what goes on behind the scenes, like what image processing actually is, and the color spaces, gamma functions, and all the values that we are applying here, right? And by the way, if you are curious, the current cube LUT looks actually like this, right? You can see how we are not like how all the values in a single row are all the same. I don't know, hopefully this comes through because this is black and white. We are loading everything into a single channel, and they are not as uniform because as I go through, they don't seem to be amazingly uniform, right? Just perceptually, I mean. You don't have to, you know, actually know, but just perceptually don't seem to uniform because previously when we created the neutral LUT, it was very easy to see how, as I scrolled down, we went from 0 to 1. Anyway, so this is just as an interesting thing. And we can actually change the size. We could change the title of this, but we're not going to. It's fine now. So this is the correct relative luminance. Now, in order for you to understand how these differ, here is what we can do. I can actually reactivate these lines with the wrong relative luminance and the average calculation. So both of these, right? I'm actually going to just comment these. Average, actually going to black and white, and then parentheses, average method. Let's do another one, which is black and white, and wrong relative lum method is what I'm going to call. And then we have the third one. So what I'm going to do now is, because we have, this is the fantastic thing about RGB, is we have actually 3 channels, right? So we have 3 channels, which means that we can utilize those 3 channels if we wanted to for data. So I'm going to grab the average, and I'm going to load the average into the first channel, which is the red channel. Then I'm going to grab the wrong relative luminance, and I'm going to load that into the second channel, which is the green channel. And then I'm going to leave the sRGB relative luminance, which is the correct relative luminance, in our blue channel. Now, if now I'm regenerating the LUT, which I'm doing right now, and it's successfully regenerated, and I reload my LUT inside Photoshop, let's just do that. You see some sort of a change, and you also see these different colors here, right? Which you might be thinking, if you are somewhat unfamiliar with the topic, is that wait, I thought we were doing black and white, so why do we have color? Well, the reason we have color is that the color actually shows you the differences between the different black and white conversions. Because we loaded these different black and white conversions into different channels, those adding together as an RGB file are actually show up as differences in the total values in a way. So if I go into the channels, and I select only the red channel now. So this is the red channel. This actually shows the average method of black and white conversion. Then if I flip to the green channel, it will show you the wrong relative luminance black and white conversion method. Look, do you see the difference? Like, this is the average, and this is the relative luminance. That's the wrong one, right? So both of those are somewhat different. You can clearly see it on the checkerboard, or the color checker. And now I'm going to switch to the blue channel, which contains the correct relative luminance. It's not going to be that huge of a jump, but you're still going to be able to tell the difference. So this is the before, and this is the after, right? So this is the wrong one, again, quote, wrong one, and this is the right one. So that, and if you compare the right one to the average, you can see the difference. You see how on the average, like, all the colors are kind of the same. They don't really have that much of a brightness difference. Whereas if you go to the wrong relative luminance or the right relative luminance, you have this, change. Now, because you don't want to click on these channels, you might be thinking, oh, so why is it good that I packed these unless it's for demonstrational purposes, which is stupid because that doesn't have any use, right? But it does have use because, first of all, using a single LUT consumes less memory, I think, inside Photoshop, than using multiple LUTs. Like, you are not using like multiple layers and you're not applying multiple calculations. And even packed, what you can actually do is you can create on top of your LUT a channel mixer layer, right? You can create a channel mixer layer, flip it into monochrome, if you wanted to, but you don't even have to, but you can flip it into monochrome, and you can just pick from the channels, right? We pick the blue channel, we pick the green filter, which is the green channel, or we can pick the red one, right? That's just exactly it. Like, that will help you like pick those channels here, and that will give you the exact conversion that you were looking for, right? So that's just the way it is. Now, as an alternative method, which is, I just recently read about it, and I'm kind of on the fence. About this, but I wanted to introduce this to you. Let me see if I can find this. Let me see, because I had this open just specifically so I can show this on stream. Sorry for the weird head position. I'm just trying to keep myself close to the microphone, and I'm still trying to turn, and because of that, I turn into Gollum. That happens. Okay, I found it. Fantastic. So, let me just pull this on the monitor. Let me see what you can see so I can see if that's actually good or not. Okay, let me just zoom in. So, something called the HSP color model, which someone claims to be an alternative to the HSV and the HSL model. And this person just basically put together like a different, like you can see it here, a different brightness calculation, which they thought were perceptually much better. So that's the last thing in terms of luminosity and luminance that I'm actually going to try out here. And they're calling it the HSP color system for some reason. It's fine, but I'm quite skeptical whether this is actually good or not. They have a sample here that doesn't really matter, to be honest, because that's for the full conversion. They are claiming that, notice that in the HSP system, the text is very hard to read, indicating that the gray delivered by that system is extremely similar as interpreted by human vision to the corresponding RGB color from which it was generated. So they are saying that the reason HSP is so terribly bloody unreadable is because their luminosity conversion makes the gray very similar to the, like, perceptually to the color that's like underneath. It's actually terrible to look at it, but you know, I thought that it would be interesting to just check it. The way they are saying that the way they were coming up with these is that they were just basically trying things, which is fantastic. Like, they were playing around. Fantastic. But that's why I'm skeptical. That's the only reason I'm skeptical, because you still need to understand some of the underlying things, and if you just like play around, it could still give you, like, you know, good results, but will it be stable enough so that you can use it in any environment and whatever? You know, that's why I'm a skeptic about this. Okay, I'm putting this back to where it was, and we can just do that. We can just use that as the last calculation here. And I actually already saved this out so that I don't have to type it out, because I don't want to bore you with all of that. So after all of this, you know what, actually, I'm going to put this on top of the average so that it's easy to find. So this is going to be black and white, and it's going to be the HSP method. I'm going to call this const float HSP. Let's call it brightness, because they were calling it brightness. HSP brightness, and it's kind of a long thingy, but it is this. So it's technically the square root of the calculation of 0. I'm actually going to put the zeros there because that's much easier to read. So it's the square root of 0.299 times red to the power of 2 plus 0.587 multiplied by the green to the power of 2. And then, you know, the rest is the blue. It's kind of the same thing, just a different number there. So let's just see this. Let's just see. I'm going to replace the average with this. Let's just replace the average with that, with the HSP brightness, and we'll see how it how it works, like whether it actually is something that's worth looking at or not. So let me regenerate this. Oh wait, I have a. Oh, I'm not using probably the average there. Let me just comment this out then. Oops, sorry. Let me regenerate this. We are good to go. And also wanted to switch back here so I can see this. Oh, regenerated the LUT. Now, I'm going to load the LUT back in so that we're reloading it. You see how the colors somewhat changed? I don't know if you are paying attention, but if you were paying attention, the colors somewhat changed. Let's see. So going into the channels, the red channel now contains the HSP conversion into brightness. So this is what it is. Oh, this is what it is. Let's zoom out. Let's look at the full picture. Okay. So let's compare that to the correct relative luminance. Not that big of a difference. Not that big of a difference. I see some difference in the color channel, in the color checker, and I actually prefer the relative luminance here. This seems slightly brighter than I would want, I think. But again, these are tiny differences. Very tiny differences. And let's compare now the HSP to the wrong relative luminance calculation. There, yeah, that's a huge difference. But that's always a bigger difference because that calculation is just wrong. Even though I like it myself, like I like this conversion, but it's like mathematically the way it was designed, or not actually mathematically, but design-wise, this is wrong, incorrect, rather than wrong. I mean, it's a valid method, right? It's still, you know, but it's a huge calculation. Like you need square root, you need power of, and you still have the multiplication and the addition. So it's a lot of, like, it's quite a heavy operation to go through all of that. So somewhat of a silly suggestion, unless you don't care about conversion or complexity. Like we don't actually. In the LUT creation, we don't care how complex it is. We can just chuck it in because it's going to calculate a lookup table. It will not have to calculate later these numbers. Like these numbers that we are pre-calculating, if it's not clear, I'm telling you, these are pre-calculated. That's what lookup tables for. It's going to be, the result is going to be looked up later, not this calculation. This calculation is going to be cached as a result. So it's going to be super fast as all the other calculations. Right. I know I'm like, this is quite heavy, but I'm hopefully not losing everyone in the sense of hopefully you guys are enjoying this. And this is something that's useful. I'm personally am like very, very into this. If you couldn't tell before, this is something that I really truly love, because I always thought that you know, us retouchers and people who are digital artists, we don't really know that much about the underlying principles and maths and everything. And we don't really need to, right? We don't really need to. But at the same time, I think it makes us better artists and better craftsmen if we are at least aware of, oh, that's like, I remember someone talking about this. That's something like that, right? That's, you know, that's what I'm talking about here. Okay. Next thing. What I'm actually going to do is I am going to package this LUT so that this will be available later. So let me rename this file, this output file here. I'm going to name this black and white conversions or something, just so that we have something different, right? So that, you know, I don't have to recalculate this later. What should I call this? Let's call it luminance utils is what I'm going to call this. I'm going to just regenerate this quickly, just so that we have, like, I have this and I can spread it around, like people can like get it. Okay. So you can replicate the code that you're watching right now, or you can just get the resulting LUT later when I put it up online. So that's the first thing. So now we have that generated. Let me check if we do have that generated. We do. Fantastic. Probably going to have to rename that later. Whatever. Actually, you know what? Let's rename the title to something else of the LUTs title, I mean. It should be HSP. Incorrect relative luminance. And what's the third one, which was the correct relative luminance utility LUT is what I'm going to call this. Oh, you know what? Let's call it conversion LUT. And I'm just going to regenerate quickly. Just 2 seconds here. Okay, I have that. So now, just as if you're curious, if I look into the luminance utils, it says this like very long title here, but at least you know what this is. It's fine. Okay. Right. So now, so that we don't really save over it, we are going to just call it saturation map LUT. It's going to be the next topic, and now I'm actually going to set util. So what we are going to call this? Oh, okay. Let me just let me just take like a small break in the sense of just leaning back, drinking some water, and just seeing if there are any questions or not. Oh no, drinking some water is just completely failed. I failed that mission. Okay. Next part. As I promised, we are going to work on saturation mapping as utility LUTs, and I want to have that as like a thing here. The last time we went through how to convert images into different saturation maps. So those were the images, but the good thing is that now we can actually utilize that and utilize those functions and principles that we talked about, and we can actually, thank you, just Windows install, update install just popped up. Hopefully the stream is going to end because Windows is going to be like, oh, sorry, I'm installing this update. Anyway, so where was I? So we went through all of that. So we have the principles. We know how to do that. And the good thing about LUTs, as I said before, and many times before actually, is we can just use the same principles that we use on pixels for LUTs. So in our case, we have the black and white conversions, right? So we have these black and white conversions, and I'm actually going to use that as a section here. So I'm going to use this as section and black and white conversion. And the reason I'm doing this is that it's easy to differentiate, and we are going to be less cluttered here, hopefully. So I'm going to be like section end. And this is the section end. So this was the black and white section. Now we are going to open our next section, which is going to be section I'm going to actually do the saturation map. Okay, I'm going to do like section end as well. Let me just do these thingies like that. All right, so more of the image processing. So what I need, I'm going to reach back to the previous code that we wrote the last time, just so that it goes actually faster, because after this it should be quite fast. You see that we have our functions here, the linear to sRGB and the sRGB to linear. Now we need a couple other functions that I'm going to pull in from the previous code base, which was actually, where was that? Oh, it was in the other files, right? So we have this this main.c, and if I go up here, the first one that we have is actually, you can see RGB to HSL conversion function. So this is going to be the first thing that I'm pulling in. What does this need? It's going to use an array. Whatever, I'll just work with that. So I'm just putting it in here and saving this. So we're going to create this LUT first, and then we're going to create the next one, and then the third one, and then we can actually package that the same way as we package the luminosity one, right? So the first one is going to be RGB to HSL. So getting the RGB to HSL is going to be just as simple as the luminance conversions, right? So I am going to make which is going to be a different syntax. So I need a float array, which is going to be HSL. Right, it's going to be HSL of 3. Oops, actually I don't need the pointer then. HSL 3 is what I need, and we are going to apply the RGB to HSL conversion to our red value, to our green value, and to our blue value, and outputting it into our new HSL variable. And then all we are doing is we just want to take from the HSL output, which is hue, saturation, and lightness. We are going to take the second element, which is saturation in this case, and we are going to output that into all the channels, just like we did with the original black and white conversion. So instead of HSB brightness, wrong relative luminance, and sRGB relative luminance, I'm just going to put in here the HSL and the second element, which is, because it starts with 0, so 0, 1, 2, we need 1. That's the second element. So I'm just going to copy this into this. This is, if you were here the last time, or if you saw this on you know, during you saw the VOD, then this is very similar, almost the same thing as the what is it, the previous stream, right? Now it's going to complain that I'm not using those variables. I'm not sure if it is it wall that complains about it. So I'm just going to delete that. Yes, okay, good. And regenerate this. So let's go back to RGB. Let me just clean this up so that it's easy to see everything. I'm going to turn off the LUT. So this is the original image. I'm going to load in the LUT now, which is actually now called set util cube, just so that you don't get confused. And nothing happens, right? But if I turn this on, look at that. If I turn this on, we have the HSL values here. We are actually displaying all of that, and I think that's fantastic. So we have the saturation map from here on out, and we can use this on any sort of an image here. I have some images that I recently opened from. Okay, this is just Kendo image. It doesn't matter what they are. I'm just going to open a Kendo image. Oh, this is a friend of mine. So let me just grab this and just put this on top of this image of my friend. And because it's a LUT, you can immediately see how it actually just turned this into a saturation map. Like, it's literally here. We just have a lot of grain, so that's why you see this like graininess here. But, you know, because it's a LUT, it's not a flat image, you can already create these saturation maps on top of any sort of an image you would want. And the fantastic thing about saturation mapping, and someone actually asked this in the previous stream, and I'm going to reiterate this because this is quite important. What would you use these saturation maps for? Well, there are plenty of things that you can use it for. You can use saturation maps for either controlling the saturation separately, so somewhat averaging saturation, or you can use saturation maps for brightening and darkening certain parts of the image related to saturation. And you can probably use it for masking as well, right? If you want to mask someone out of a certain background, they are in front of a certain background, and that background saturational value is very different from the person's saturational value, then you can add that as an additional mask for your cutout, because, you know, for cutouts you're looking for differences. So here is the HSL version of that. Now, as you can see, this was 2 lines of code and that function up there, and we have HSL. So that was the HSL. I'm going to actually comment this, saying HSL saturation map. Okay, next one is going to be the HSV, or sometimes called HSB saturation map, right? That's what it's going to be. I'm going to go back into the previous stream's code, and I'm just going to copy the RGB to HSV. So you can just pause here if you want to copy this for some reason. But you can find it a lot of places. This is just RGB to HSV conversion, very simple. And we're just going to do the same thing here. I'm going to copy these lines just so that I don't have to type myself. And instead of HSL, I'm actually calling these HSV. That, and down here, I'm going to rename these to HSV as well. And now if I regenerate the LUT, which I just did, and now pay attention to the image, and I load in the saturation, the other saturation, like the same thing, I reload the LUT just with the new saturation mapping. Look at the difference. This is very different, because in HSV space, these are the saturational values that you encounter in this image. So you see how important this is to be able to use and utilize the right algorithm for your saturation needs, right? Now in this one, by the way, what I can do is I'm just going to demonstrate what I talked about before, which was, what do you use this for? Well, as I said, you actually use this for either to gauge saturation and see how even the saturation is, for example, in skin or some other parts of your image. But the other thing that you can actually do is you can just take this and let's just create a mask out of this, right? Let's say that we want to desaturate the values that are too saturated, right? So we want to desaturate the image, but we want to desaturate the saturated values more. So somewhat of a vibrance, if you will. So if I created a new hue and saturation adjustment layer and I'm on the mask, right? Then if I go into image, apply image, I'm actually going to set this to normal, the blending, but I think it would work on multiply as well. I'm just hitting OK with all the other default settings. You can see that this is if I switch to the mask, it's exactly the same thing. So if I turn off this thing and I switch to the mask, then we have this inside the mask of the hue and saturation layer. And now if I start to bring down the saturation, you see how it's actually so gentle. It starts to desaturate values that are actually more saturated. So as I bring it down to, let's say, like 40 or something, we somewhat get this nice even saturational values around in our image. And I can actually double check this by putting this LUT, this saturation map LUT on top and turning this on. And if I turn this underlying hue and saturation layer on and off, you can see how the brighter areas are getting closer to the darker areas. So that means that we are bringing the saturational values closer to one another, right? So if I were to, let's say, turn this off and duplicate the hue and saturation adjustment layer, go into the mask and reverse the mask now, right? So now the mask is reversed. Then what I could do is... and grab the saturation and start to boost the saturation here, then we are actually saturating the less saturated values. So again, we are somewhat creating some sort of a vibrance by being able to bring these things together. So this was the before, you see the contrast, and this is the after. Like we are kind of like minimizing the distance between those values here. And again, this can be used quite powerfully. The other thing that I showed, I remember, is if instead of a hue and saturation layer, if you were to use, for example, a curves adjustment layer. So let's say I create a curves adjustment layer, turn on the saturation map LUT. I do the same thing. I apply the mask into the curves adjustment layer, right? So I can turn this off now. So it's inside, like if I click on the mask, this is the mask. And now what you can do, and this is quite useful in film emulation, you can kind of start to pull down the more saturated values to give them some depth, right? Some density, if you will. So this way you're creating, and you can see it's quite pleasant. Like this is before and this is after. It doesn't really darken the image. It darkens it a bit, but it darkens it quite selectively, and it darkens the values that are very saturated. So if I pull these down, you can see how it actually influences those saturated values. What actually turns into very beautiful color is if you look at the, I don't know if you can you actually see this? Yeah, you can. If you look at the cyan and blue values. So this was the before and this is the after. Like it just makes them look quite nice. Or you can actually play around with the luminosity as well if you wanted to. This is luminosity, this is normal. But yeah, this is... I like this effect. This adds some density. Like look at the image now. I think it has a very nice density, whereas before it was kind of light. But now we are adding some density, but not everywhere. It's not uniform. So it gives you a lot of power if you have like access to these saturation maps and all sorts of maps. Utility LUTs are very, very useful. And the reason LUTs are much better than most things is because LUTs can adapt to your images and your resolution and everything. Of course, they interpolate, but still, it's good. Okay. So this is the usefulness of it. Now, the third thing that we actually, I wanted to actually explore is the very complicated one, which was the multiple conversion one, where we eventually get to the HCL or or LCH version of this, right? Where it's still saturation, but it's a much more perceptive or perceptually uniform saturation, right? So if you were not here the last time where I built the whole thing up to the finale, and I completely utterly failed because I forgot a single value, then we're going to repeat that without me failing. But and also with it being a LUT, so being very versatile and usable, not just a single image itself. But it's complicated, I warn you. And the reason it's complicated is because the first step is we need to linearize the sRGB. So we need to turn the image into linear. Then the linear values need to be turned into XYZ color space, which is this common color space that we use usually to convert between colors. Every color can be converted into XYZ, and XYZ can be converted into every color space. So that's the mutual, that's like the bridge in between all the color spaces. And then from this common XYZ color space, we are going to convert into a color space called LUV, which is very, very similar to lab, which you're probably familiar. It's a perceptually, at least it tries to be perceptually uniform color space. And that's fantastic for us. And then that perceptually uniform color space, we are actually turning into LCH or HCl. It's very similar to HSV. HSL is just LUV's cylindrical system. I know I'm throwing a lot of words at you, but bear with me. So I'm just going to copy a lot of these functions just so that I can use them. Again, pause them if you want to copy. Pause the video if you want to copy them. But I explained all of this last time. I mean, I didn't go too much in depth because I didn't want to bore everyone to death, but I somewhat explained most of this. So, do we have... Okay, so we already have this in here, so we don't need to do that. Okay, so the first step we are going to do is we are going to sRGB to XYZ conversion is the first step, right? So we are going to get a variable. We are going to be calling it actually XYZ. It's also a 3-component variable, and we're just going to use sRGB to XYZ, which a function we have, and we're using the red, green, and blue, the default values that we have, and we are just feeding in this output XYZ. Fantastic. The second step, as I said, is actually going to be about XYZ to LUV. I know it's a lot. Conversion. And we need to do the same things. I'm just going to copy this. These two lines are going to repeat, except I'm going to go and call this LUV, and this method is actually called XYZ to LUV. Okay. And then the last step, again, I know it's a long thing, and you don't have to remember all of it, is we are converting LUV to cylindrical, which is going to be LCH. So it's LUV to LCH. I think it's written like this, conversion. And I'm copying the same thing. I'm just going to name this LCH. And it's going to be probably LUV to LCH. Yeah. Okay, good. Fantastic. So after all of that, we are going to be in LCH space, and that's what we are going to output here. So instead of HSV, we are going to be typing LCH. Now, the thing that I forgot the last time is that this needs to be divided by 180, right? To normalize this, we need to divide it by 180. I don't actually remember how in the past I got to 180. It's just something that I've been using. I actually need to look that up if that was my finding or if that actually is I got it from somewhere. But we need this is the point. So we are outputting LCH now. So I need to regenerate the LUT, which I'm doing now. Regenerated this, and hopefully, again, this is the big finale. Please don't let me down now, because the last time you did. I mean, I let myself down, but we'll see. So let me just double click. Let me just reload this single LUT, please. Of course. What did I mess up? Don't tell me that I messed this up again. I was working so hard. Oh, I know what I messed up. Yeah, I'm dumb. I'm so dumb, but I know what I messed up. It's good. We're still going to build to the grand finale. Please don't. Please don't hate me for this. But what I messed up is that you see how I was doing the conversion and then kept feeding in the red, green, and blue all the time. This is not what we need. We need to chain this, right? So because so XYZ we are inputting red, green, and blue, but for the XYZ to LUV conversion, we need to input the XYZ, right? So this is going to be XYZ 0. This is going to be XYZ 1, and this is going to be XYZ 2, right? So I'm just going to copy all of these, and in here, oops, we are actually going to need the LUV. So we are chaining this in. So first we are adding in the RGB values, then we are converting that, and to the second one we are adding the converted values, and to the third one the again converted values. So I was building to this finale, but now the second, let's try it again. Drum roll, I guess. Hopefully this will work. This should work, right? Unless, again, I mess something else up. Yay, it works. Fantastic. So this is LCH. Now, I actually can go into just the levels and see if we can just like pull this up a bit more. Right. It's very similar to the previous HSV conversion, but it's still something different. But we have these different saturational maps here. I'm quite glad that I didn't mess it up again. I would have been so sad. I was sad for a week after that. I was like, oh no, I was building onto that and I messed it up. But now I'm okay. So we have these three options that we can use for saturational mapping. And because we are so smart and we created three different options, we can actually bake these three options into a single LUT. And the way we do that is exactly the same thing, same way we did with the luminosity conversion. So I'm going to take the first component here, and I'm going to put HSL's saturation in here. And I'm going to take the second component, which is green, and I'm going to actually output HSV's second element. And I'm going to let the third one be the LCH. Now, if I resave this, it's actually resave and regenerate, and I reload inside Photoshop. You're going to be met, at least you should be met with, where is that image? With this image, with this colored image. And except in a LUT form. So it's going to be a LUT and not an image. So I'm going to reload this because I regenerated this already. And it's, yay, look at that. We made this happen. And the reason you see this like very different colored image is because we packed these different LUTs into all the components that we have, right? So if I go into the channels, this is the RGB output, but if I select the red, this is actually HSL. If I go into green, this is HSV. And if I go into blue, this is the blue channel. Now again, you might be asking how it is that you can actually extract these, and very simply, you can just create a channel mixer, and you can just like select, let's say, the red filter, which is the HSL value, right? And you can just clip this to the color lookup, right? So this way, if you're working with HSL, you want to work with the HSL map, you can just select that one. If you want to work with, for example, the HSV, which we packed into the green channel, then you just select the green filter. Or if you want to work with the LCH, then you can just switch to the blue filter, right? And for some reason, if you want to combine them, you can just like go to like the infrared, or you can go to the orange filter, or you can go to the yellow filter, and they will give you a certain result. Those will be much more artistic and less mathematical. But you know, if for some reason you need them, then just go for them. That's just how simple it is. But with the single LUT now, you have the power to go through the whole thing and be able to, you know, apply multiple different conversions to your images. And yeah, that's actually what I was building to. I know it's a lot. I know, it's a lot. Isn't it fascinating though? I still think it's like fantastic. And now, just as an interesting thing, let me just copy this into the image of my friends along with the channel mixer, just so that you can see like a different image. And I'm just deleting this other color lookup here because it's a LUT. I'm trying to prove that it's a LUT, right? So this is the colored thing. So you need the blue is this one. This is the LCH. The green, which is the HSV, is that one. And if you want to go for the HSL, then this is the red one. So you can just cycle through all of these. You can see how the LCH is just so representative of the whole image, and it breaks it less. So that's why sometimes it's good to use for saturation maps, because you have some less breakage of the image. But again, this is a very grainy image. If you see, this is quite grainy. So it could be anything, but yeah, that's the something that we created. Now, I think what we need to do here is we need to give this a nice title, just like we did before. So let's just give HSL, HSV, and LCH saturation map utility LUT is what it's going to be the name. And we can just call this, well, for now, that could be the name, and we can just regenerate this. And the fun thing about this, the way we created this whole thing, is technically, if I haven't messed anything up, then we can just change the size to whatever. We can just use like 16, for example, and I can regenerate this, and it's just going to be a way more compact LUT. So now if I go into the set util cube, you can see it's 16, and the amount of lines we have is only 4,000, right? It's only 4,000, and instead of like the 32,000 or something, it's not going to be as accurate. So if I load this in, you should be noticing a difference because of the interpolation, but it's probably going to be okay, I think. I actually never tried 16, so like that low of a LUT size. Let me just see. You see, there was a slight difference, but it's still usable. So if you want to save some processing power, some memory and everything, then, you know, we could be just like using like small outputs of these LUTs, and then it still works the same way. Like I can still switch to LCH and everything else. Alternatively, if you want to be very, very precise, but it's you know, it's going into like overkill territory, you can go for like 64 or something. We can regenerate this at 64, and that's going to be way, way bigger. Now, if I check the last line, that's going to actually be 262,146, right? So it's like from 4,000 we went up a bit, and now if I reload this again, you will see a slight difference. It shouldn't be like a huge difference. I don't think so. Yeah, it's still reloading, by the way. Oh no, it's reloaded. It's like I personally didn't see a difference, and I'm not saying 16 is fine. I'm just saying that it's, you know, but now it's very precise. So yeah, that's a fantastic world of programming. Like creating LUTs through programming and coding and everything. And the funny thing is that we could add so much more functionality here. Wait, I can't actually, I set this up terribly. Hi Victor, been watching silently because it is a bit above me, but it was actually instructive, and this 3-in-1 LUT is really interesting. Oh yeah, thank you. That's what I understand how the people who usually watch my streams are more, you know, their expertise lies in some other fields like retouching, photography, lighting, and composition, all of those things. And maybe programming is not something that they do all the time. But I think if you can look past that, it's a lot of lines of code and some things that you don't really understand, and you're able to look beyond that and just try to concentrate on how things work. I think that actually helps you be a better photographer, a better retoucher, and a better digital artist all around. Just think about it this way, in the sense of knowing how color spaces work and how conversions from one color space to another works can actually help you inform your decision on, like, oh, which color space should I use for this? Which color space should I use for that? Is it possible to convert from this? And what am I losing if I convert from that? And you don't have to know the conversion code or the conversion matrices or anything. You don't have to know those. You just have to understand that, okay, so the reason this wouldn't work well is because this space is that size and that space is this smaller size. And if I do that, I'm actually cutting off, like I think it's fascinating. It's just, and it's for me, for myself, who's a professional in the retouching field and who's a professional in the field of image processing and somewhat trying to be very knowledgeable about color science and everything. I believe I can provide a better service for my clients because of my my knowledge and because of what I understand and know, and because of the tools that I can create to help people who can't create these tools and people who need these tools, like myself as well, by the way. Like, I need these tools. I use these tools. I wouldn't show you something that I wouldn't use myself. Anyway, this was a long thing. I just appreciate you watching is what I'm actually going to say. And as I said, I think this is it's fairly important, if you don't mind me saying that. Now, I know that we only have like a handful of people here because I scared everyone away. But if the people who are still here, if you guys have any sort of questions, I'd be more than happy to answer. Even if it's, and don't be afraid to ask questions. Like, there are no bad questions here, is what I'm trying to say. No silly questions, no bad questions. All questions are valid questions, and I would be very happy if I can to answer those questions. But yeah. Otherwise, we created a LUT. We programmed a LUT in a software programming language. You could do this in JavaScript if that's something that you understand more, or anything. You can program this in anything. The point is the output. You can actually write these by hand, but that would take a long time. But yeah, hopefully this also gives you an idea of how LUTs work, which I know it's something that I talk about a lot, but it's still, I think of it as like an important topic, because otherwise people just throw LUTs on things. They use it as like filters, right? Which is fine. You can use that. Don't be afraid of using it as like a filter. Don't be afraid of like, there are no unconventional ways. I'm just saying that if you're able to be aware of what you're doing, I think that's going to elevate your work. But that's just my opinion. Right. So we generated 2 LUTs. We have luminosity conversions. We have saturation maps. It's something that we can play around with. It's something that we will be able to use. I'm going to upload this somewhere. I'm actually, with this one as like an exception, I might actually keep this on YouTube. I might keep this on YouTube. We'll see. Anyway, I think there are no questions, but that's fine. I do appreciate all of you being here, and I do appreciate all of you watching and supporting me. And hopefully, in turn, I can support you by giving you what I know, and hopefully this is helpful. Fantastic. No questions, I guess. So, in that sense, I am going to just say my goodbyes, which is fine. Still assimilating. Fair enough. I'm not trying to put anyone on the spot here or anything. I appreciate it. No, I appreciate it. Again, it's just, I find this very interesting, very fascinating. I'm happy to be here, and I'm happy if there is a single person listening to this. It's, I usually, because I'm a crazy person. If I'm alone and I program, I'm creating tools and LUTs and everything, I sometimes have to talk to myself and just talk things through and work things through. So this is basically the same thing. I'm just working on something that I find useful and fascinating. But anyway, You know where to find me if you have any more questions during the week. I might stream during the week. We'll see. If I do, it's just going to be a surprise, and it's fine if you're not here, and it's fine if you just watch it later, or if you know, any of that. But yeah, have a fantastic weekend, and then have a fantastic week, and we'll see each other hopefully. If not sooner, then maybe next Saturday. And actually, I'm not sure what I'm going to be talking about. Probably something image processing related. Thanks so much for being here. I enjoyed our time. Bye, everyone.